Okay, let's dive right into this by challenging an assumption I think a lot of us unconsciously hold. It's the idea that AI is just weightless software, right? A magical brain just floating out there in the digital ether. When we interact with a chatbot, it feels instant, it feels infinite, and entirely virtual. But we really need to ask ourselves, where does that intelligence actually live?
Well, there is a massive divide between this concept of the ethereal cloud and the absolute reality of heavy metal and liquid coolant. The magical code of AI, it's actually entirely bound by massive, multi-ton, thermodynamics-heavy hardware. We are talking about physical limits that are incredibly tangible.
Welcome to our Explainer. Today, we're going to completely demystify the colossal physical infrastructure that makes large language models possible. We are looking at a global ecosystem that is arguably the most complex and capital-intensive manufacturing network in human history. It's wild.
So, here is our roadmap for the journey. We'll start with the physical reality of AI, trace the 3 epochs of computing, examine the geopolitical tripolar axis, dive into how we are hitting the physics wall, and finally look ahead at the future of hardware and energy.
Section 1. The physical reality of AI, escaping the cloud.
The absolutely crucial point here is that software logic isn't the limit anymore. Generative AI is actually bottlenecked by thermodynamics, literally, the sheer heat generated by these chips. It's bottlenecked by copper signal integrity because sending data through copper wire degrades insanely fast at hyperspeeds, and it's bottlenecked by nanometric quantum tunneling, which is the absolute limit of CMOS silicon scaling. You know, when you shrink transistors down to just a few nanometers, electrons literally start jumping barriers they aren't supposed to. It is an engineering nightmare.
Section 2. 3 epochs of computing, from CPUs to chiplets. If we trace our journey, we started in Epoch I with standard CPUs, completely governed by Moore's law and Dennard scaling for serial tasks. But then we hit the 2012 AlexNet breakthrough. That triggered Epoch II, proving that the parallel processing power of GPUs, which, remember, were originally just for graphics, was vastly superior for the heavy matrix math required by machine learning. And that brings us to today, Epoch 3. Trillion-parameter models are so incredibly massive that traditional monolithic chip designs, well, they literally collapse under their own size. We've hit the reticle limit, which is the maximum physical size a chip can be printed, so we've firmly entered the era of heterogeneous compute and advanced chiplets.
Section 3. The geopolitical tripolar axis, the global division of labor.
Building these modern AI systems requires a highly synchronized, profoundly concentrated global ecosystem. Think of it like human anatomy. The United States acts as the brain, creating the architectural blueprints and IP. Taiwan is the muscle and nervous system, physically manufacturing the chips and packaging them. And South Korea acts as the synapses, providing the volatile memory that feeds data directly to the processing cores. Without just one of these anatomical parts, the entire global progression of AI just stops.
Let's break this down a bit more. American companies like NVIDIA and AMD are fabless. They design the logic and the software stack, absolutely, but they don't physically manufacture the chips. They offload that immense capital risk to Taiwan, specifically TSMC, which holds a near monopoly on high-end fabrication, while system integrators like Foxconn build the actual server racks. Meanwhile, over in South Korea, firms like SK Hynix and Samsung dominate high-bandwidth memory, or HBM, which basically resolves the major bottleneck of getting data into those logic cores fast enough.
Each player in this space has a very distinct, aggressive strategy. NVIDIA and AMD monopolize those high-margin compute algorithms and software ecosystems. But hyperscalers, like Microsoft, Meta, Amazon, they aren't just sitting on the sidelines. They're pivoting toward their own custom ASICs to break free from vendor lock-in. Over in Taiwan, TSMC maintains its 100% monopoly on high-end AI accelerator fabrication. And South Korea's SK Hynix, they focus heavily on aggressive yield optimization in 3D DRAM stacking. They are literally stacking memory chips on top of each other and punching microscopic holes through them to pass signals. It's absolutely fascinating.
Section 4. Hitting the physics wall, engineering at the extremes.
208 billion? No way, right? That staggering number is the amount of transistors packed into just a single NVIDIA B200 GPU. To even make this happen, the supply chain relies on extreme ultraviolet lithography from ASML, using a highly customized 4-nanometer process. It requires stitching 2 massive dies together to act as a single chip, just to fit all those transistors in.
But all this density results in an absolute thermal nightmare. 120 kilowatts. That is the max power draw of a single NVIDIA GB200 server rack. To put that into perspective, a standard enterprise data center rack only uses about 5 to 10 kilowatts. The engineering challenge to supply this kind of power, we're talking over 1,000 amps at sub-1 volt levels, means engineers literally have to stick the voltage regulators directly underneath the GPU on the reverse side of the motherboard just to prevent the copper traces from melting. Because traditional air cooling completely fails at these densities, the supply chain had to invent entirely new fluid dynamics. Air cooling just doesn't cut it anymore. Now we're dealing with direct-to-chip liquid cooling. Cold plates are mounted right onto the silicon. Engineered coolant runs through microskived fins to absorb the heat, and then that heated fluid is pumped out to an external heat exchanger. Data centers are literally having to redesign their structural flooring from the ground up just to handle the multi-ton weight of these liquid-cooled behemoths.
Now, to feed data into those incredibly dense compute engines, we rely on TSMC's 2.5D CoWoS packaging. It's like a giant microscopic puzzle. Logic dies and HBM stacks are placed side by side on a passive silicon interposer. They are connected by solder microbumps and literally millions of through-silicon vias to route signals. This architecture achieves a massive bandwidth exceeding 8 terabytes per second. This is exactly how the industry broke that physical reticle limit we talked about earlier.
But here is the kicker. AI's availability right now isn't actually held back by printing the silicon. The severe bottleneck is TSMC's CoWoS packaging capacity. The equipment required to align and bond these microscopic components is so highly constrained that lead times are extending past 12 months. This is the real choke point of the entire AI revolution.
Furthermore, we are physically maxing out standard materials. When you try to push data at 224 gigabits per second, copper wire simply fails. The signal suffers massive insertion loss, limiting travel to mere inches before degrading completely. Plus, trying to run thick bundles of copper cables inside these server racks causes catastrophic airflow blockages. We are hitting the absolute threshold of what copper electrons can do.
Section 5. Future Hardware and Energy. The 36-60-month horizon. So, to sustain AI's growth toward artificial general intelligence, the supply chain needs some systemic, physics-altering paradigms. First up, glass substrates. Current organic films warp under extreme heat, so the industry is shifting to ultra-stable glass. Second, co-packaged optics. To beat that copper bottleneck, we're replacing electrons with photons, literally putting lasers directly on the chip to transmit data at the speed of light. And finally, power. To run these massive future setups, hyperscalers are seriously looking at small modular reactors, next-generation nuclear fission built right next to the data centers.
This quote perfectly summarizes the ultimate reality check for the industry. The supply chain bottleneck will shift from silicon fabrication to energy generation. We are rapidly transitioning from a silicon crisis to a sheer global energy crisis. The blueprints for the next era of AI aren't just calling for new chips, they're demanding entirely new gigawatt power grids to sustain them. So, I want to leave you with this final provocative thought. As we look at this immense tripolar supply chain, the liquid-cooled racks and these multi-ton data centers fighting the laws of thermodynamics, will the future of AI be constrained not by silicon, but by global energy generation? Consider that the next time you casually ask a chatbot to generate a recipe. What physical cost did the electrical grid just pay for your answer? Thanks for tuning into this explainer, and keep questioning the technology around you.